Let's record it. Okay.
Yeah.
So these are nicknames of system.
Okay.
Whether you write a transfer function, impulse response, magnitude response, phase response, pole zero diagram, whatever you say, it's the same system that you're talking in terms in a different ways. Like h of z is a nickname of a system in a frequency domain. Okay. Now I just give you one example. Supposing if you have h of z, now you can just like refer to these things. H of z is a transfer function. If I give you a transfer function like this, 1 plus 2z inverse plus 3z raised to minus 2, 4z raised to minus 3. Okay. If I take an inverse z transform, I'll get h of n. And h of n is going to be 1, 2, 3, 4. Do you understand why?
Yeah.
And this is an arrow. Arrow says this is n is equal to 0.
Mm-hmm.
We already know this is a transfer function. We know this is an impulse response. And to be precise, this is FIR.
Could you write that equation again? The equation that goes from that normally would go from impulse response to transfer function.
Okay. The formula is here that if you have h of n, this is basically a z transform formula. That when you have h of n, you take a sum of all n's and then attach z raised to minus n, and that's how you get h of z.
Okay.
Is this the equation you're talking about?
Yeah.
This is a z transform formula. Okay.
Yeah.
So if I just plug in the values from h of n, I can get this.
Yeah. Okay.
And from h of z, I can go back also anytime. So it's always to and fro.
Yeah.
Now coming back to the point, this is important. That it is FIR. That F stands for finite. And IR stands for impulse response.
Okay.
Okay. So now, what happens here is, if h of n, which is impulse response, is either symmetric or asymmetric, we get linear phase response. And it's a big deal because when you have a linear phase response, it results in distortionless output. So it's a good thing.
Okay.
Linear phase response is good. Okay. And linear phase response is possible only when you have either symmetric or asymmetric h of n.
Okay.
Okay. So the first one that we have, the first case, h of n, this is not a symmetric one. Is 1, 2, 3, 4 symmetric? It is not. So I'll just show you. If I have to plot this h of n, the plot of h of n would be n was
is like if each side is the same exact number
correct
on sides, right?
It's like this one. Okay. So not symmetric or asymmetric. Okay. So now I'll give you the examples. FIR symmetric. The example of symmetric is h of n equals say 1, 2, 2, 1. So if I plot this, it's going to be 1, 2, 2, 1, and that's symmetric.
Okay.
Or it could be h of n 1, 2, 3, 2, 1. If I plot that, it is going to be 1, 2, 3, 2, 1, and that is also symmetric. Symmetry across.
Yeah.
All right. Or it can be FIR asymmetric. And FIR asymmetric would be, the example of this thing is going to be h of n is equal to, say you have 1, 2, minus 2, minus 1. Do you understand why that is asymmetric? It's 1, 2, minus 2, minus 1.
Could you go a little bit down?
I'm sorry, but I hope you get the, there's no space. Okay, I'll write here.
Okay. No,
1,
that's fine. That's fine.
You get the point, right?
Yeah. So because it's the same value, but it's just negative now.
Yes, yes. 1, 2, minus 2, minus 1. That's asymmetric. This h of n. Or it could be h of n as 1, 2, 0, minus 2, minus 1. If I plot that, it is going to be 1, 2, 0, minus 2, minus 1. This is asymmetric.
Okay.
Now, all these have linear phase response.
Okay.
So all of these will have linear phase response. So the condition for linear phase response is you have to have either FIR symmetric or FIR asymmetric, and you will end up with a linear phase response.
Okay.
That's it. That's the answer to that question.
So okay. The question again was: suppose linear phase is required of a filter. What type of filter can be used? So what would I? What do we say? What type of filter?
This FIR symmetric or FIR asymmetric?
Okay, so those are the type of filters.
Yes, yes.
Okay, FIR symmetric. Okay,
This
gotcha.
is also FIR. This one here. This is also FIR, but it is neither symmetric nor asymmetric.
Okay, so it has to be symmetric or asymmetric.
Symmetric or
Okay.
asymmetric, and then you will definitely get a linear phase response.
Okay. Okay, got it. Let's put question 5 somewhere next to that, so when I come back and look at it.
Question 5.
Okay.
I have the recording of this thing, so it's gonna be
Okay.
I saved it as well.
Okay, that's good.
Now I'll clear this.
What other ones were easy?
Question 5 done, right?
So, okay, 5's good.
Yeah. Now, the easiest question that we can deal with, we can do question number 9. That's easy.
9. Okay.
Question number 9. The sequence 0.4 raised to n u of n, find its DTFT and 4-point DFT.
Okay.
It goes like this. Let x of n is equal to 0.4 to the n un. Un is unit step signal, and that goes from 0 to infinity.
Okay.
Yes or no?
Yeah.
So now, look, first of all, you have to understand that x of n is a sampled version of x of t.
Okay.
You know round bracket and square bracket story?
Yeah. Okay.
That's the notation. Okay. Both of them are time domain. This is also time domain. This is also time domain. One is not sampled, another is sampled.
Okay.
On x of n, you can do z transform. And you will get x of z. Do you see round bracket?
Yeah.
Because it is not sampled yet. Now, there's one more transform, which is DTFT, which you get x of e to the j omega.
Okay.
Okay, and this DTFT is no rocket science. In this x of z, you simply put r equals 1. I'll explain this better later on. Just bear with me for a minute. And then now you can sample this as well. And then you get x of k. So now, do you see square brackets? This is called as time sampling. And this is called as frequency sampling. We know the relation of time sampling is t is equal to nts. That's the mathematical form of time sampling. I taught you this last time. That's like the expression for time sampling.
Okay. Yeah.
You have an expression for frequency sampling as well. And that's do you see this is a relation of t and n? Do you see this is a relation of t and n? You see t and n. Same story here. You get relation of omega and k.
Okay.
Okay. And the relation is omega is equal to 2 pi k by n.
Okay.
Now, will you read the question again?
Okay. The question: if a sequence is 0.4 raised to the n un, find its DFT and 4-point DFT.
Okay. So understand, you have this. Yes or no?
Yeah.
So now from here, you have to find out first Z transform. Then in that put R equals 1. And then from here, you use this formula. And then you'll get this. By the way, this is DFT, discrete Fourier transform. So from here, we have to go here, and then we'll get this.
What about the 4-point? What is that?
Yeah, I'll just show you in a minute.
Okay.
So 4-point is basically this n is 4.
Okay.
Find its DTFT and then find its DFT, right? So basically, we're supposed to find out this, and we are asked to find out this.
Okay.
Get it?
Yeah.
So we're going to follow this path. Now from here, we will go here. From here, we will go here. And from here, we will go here. That's the path I'll be following. You will know when I solve. Just see how that works. But this is the basic concept of the whole thing.
Okay.
I'm solving the question. Okay. First is, let's solve this. This is by, the solution goes like this, by Z transform formula. Okay. We have a formula for a raised to n u of n. Do you remember? The Z transform can be directly written as Z divided by Z minus A.
Yeah. Yeah.
And then there is ROC also. We don't need ROC as of now. But then by Z transform formula, I can directly write down x of Z. I should write square bracket here. Tell me x of Z. Z upon Z minus 0.4. I use this.
Yeah. Yeah. I got you.
Okay. So once you get that, well, there is a relation of Z and omega as well. Like there is a relation of omega and K. Do you see omega and K? There is a relation between Z and omega as well. And the relation here is, actually, I should not write R equal to 1 here. The relation between these two is Z is equal to R e to the j omega. And for DTFT, you will put R equals to 1. So you know that Z is equal to R e to the j. Oh my God. We can do that. Okay. What we'll do is let us get this in a negative power. So let us multiply and divide by Z inverse on over here for x of Z. It just makes our life easier. I'll show you how. Now you have x of Z equals 1 over 1 minus 0.4 Z inverse. I just multiplied. Okay.
Okay.
Now here, let's put Z equals R e to the j omega, and let's make R is equal to 1, because R equal to 1 amounts to DTFT.
Okay.
So making R equal to 1 and putting Z equal to e to the j omega is nothing but DTFT.
Okay.
So I get x of e to the j omega. I just replace Z by e to the j omega.
Okay.
You see I'm getting from here to here?
Yeah.
All right. So I get this as 1 over 1 minus 0.4. This is e to the minus j omega.
Okay.
Now, after I do this, the next step is I'll put omega is equal to 2 pi k by n.
Real quick. On the e to the negative j omega, the only thing different that we're doing there is we're substituting the value for z by the negative, actually e to the positive j omega.
And then it became negative here.
Okay, got you. Okay.
Okay. Now, did they say n the 4 point?
Yeah.
So the n is 4.
Okay.
Okay. Now we'll write this as x of k. The entire e to the j omega will be replaced by k, or you can just write like this. You can write e to the j omega is 2 pi k by 4.
Okay, the omega is okay. Got
Yes,
you.
omega is replaced by 2 pi k by 4. But now this entire term has got only k as a variable.
Okay.
Everything else is constant. E is constant, j is constant, 2 pi, it's just, everything is constant. So I'll just write it as x of k for convenience.
Okay.
Because it will depend on k. K is a variable, everything else is a constant.
Okay.
Now, let's do that. We're going to get x of k now. And look, this has to be written as square bracket.
Okay.
Because this formula is nothing but frequency sampling. This formula is nothing but a frequency sampling.
Okay.
That is over here. It's a ditto same thing what we did for time, just that we're doing it for omega. And omega is frequency.
All right.
So I get x of k. Now x of k, I just have to write, I just have to replace omega as 2 pi k by 4, which is omega equal to pi k by 2. 2 2s are 4.
Okay.
So now tell me what you will get. This is as 1 over 1 minus 0.4 e to the minus j, e to the minus j, that will be pi k by 2. Is it correct?
Yeah.
Okay. Now, once you get that, k is going to go from 0 to 3. Count 0, 1, 2, 3. There are 4.
Okay.
So it's going to go from 0 to 3.
Okay.
So then let's put the values. At k equals 0, x of 0 is going to be 1 over
1 over 1 minus 0.4 e to the
that's just
negative.
that's just 1, right? E to the 0 is 1.
Oh yeah, yeah, yeah.
So you're going to get 1 over,
So all we're doing is substituting the k for 0, right?
yes.
Okay.
As I told you, k is going to go from 0 to 3.
Okay, we're doing that 4 times. Okay.
So this becomes 1 minus 0.4 and e to the 0 is just 1. 1 minus 0.4 is 0.6.
Okay.
That's 1 over 0.6. Now put k equals 1. You will get x of 1. Tell me.
Okay.
1 minus 0.4
0.4 e to the
negative
negative j pi over 2.
over 2. Do you know e to the j theta? It's an Euler's relation. E to the j theta is cos theta plus j sine theta.
Okay.
Yeah. And you can just like remember this, that cos of, well, I'll just show you how that works. What if I put theta equal to pi by 2? E to the j pi by 2. By the way, if this is plus, then it is plus. If this is negative, this is negative. This is called as Euler's identity.
Okay.
Euler's relation or Euler's identity. This is a standard relation in math.
Okay.
Now, if I put theta equal to pi by 2, it becomes e to the j pi by 2. That will become cos pi by 2. If it is plus, then it is plus. If it is negative, then it is negative here.
Okay.
J sine pi by 2.
Okay.
Cos 90 is 0. Sine 90 is 1.
Okay.
E to the negative j pi by 2 is minus j. This becomes 0.
Yeah,
This
yeah. I get
becomes minus.
Okay.
That's the value I'll replace for this.
Okay.
Then I get this as 1 over 1 minus 0.4 j, and then this becomes plus.
Okay.
It's a complex number.
Yeah.
So whenever you have a complex number, we have a practice of rationalizing it, right? 1 minus 0.4 j, 1 minus 0.4 j.
Okay.
You rationalize, right? So
Yeah.
this as 1 minus 0.4 j divided by 1 plus 0.4 j, 1 minus 0.4 j is going to be 1 plus zero point 0.4 square. Okay, do you know this? A minus IB times A plus IB is A square plus B square. Do you know this? A minus B, A plus B. That's A square minus B square.
Um, looks familiar, but off the top of my head right now, I don't quite remember. But
Yeah.
I'm sure I've done it many times. It's just
Yeah, it's just like multiplying the whole thing and then becomes, you just like solve and you'll get it. So as of now, you can just like trust me about this.
okay.
So I'm using this result. A minus IB, A plus IB is A square plus B square.
Okay.
So I get this as A plus IB, A minus IB. So it's going to be A square, 1 square plus zero point 0.4 square.
Okay.
I get this as 1 minus 0 0.4 j divided by 1 plus, what is the 0.4 the whole square? 0.16, is that correct or no?
We just multiply these two.
Yes.
Oh, for the 0.4 square. Yeah. Yeah.
0.16, right? So then the answer is going to be, this whole term will become 1.16. So 1 over 1.16 1 minus 0.4j is this answer. Got it?
Let me see. Hold on. Let me kind of re-go over it real quick. Okay, so we start here, and then so we start at e to negative j
Uh-huh.
over 2,
Mhm.
and then from there we get our 1 over 1.4j.
Yes. That's
That
because
turns into
the minus j
j
pi over 2 is negative.
this formula. Okay, and then we want to rationalize that.
Yeah.
So okay, one minus. All right, and here. So all we do is just basically cross multiply to get our 1 squared plus 0.4 squared.
Yes. And that's 1.16. And the numerator remains like that. 1 minus 0.4j.
So why is that one on the denominator a plus instead of a minus?
Oh, well, this is the formula here.
Okay.
And the
Okay.
formula
Okay.
is a plus.
Okay.
That's how I got this plus.
No, I mean for the first one, the one before that.
Okay.
That that one. Yeah.
I just
Why is
why I multiplied by these two? Are you asking this? Why did I do this?
no. I can see that, but the next result of that, why is the denominator a plus?
Because this is a plus ib, a minus ib, and then when you multiply these two, it becomes a square plus b square, which is this formula.
Oh, okay, okay. I was trying to see what the difference between the top one and the bottom one was. Okay.
The top one doesn't have I,
Doesn't have I, yeah.
and then I square becomes minus, and that's why that minus becomes plus.
Okay.
Do you know I squared is minus one?
Yeah.
So
Haven't had to use that for a while, but yeah.
right. So
Okay.
that's how I got this answer. And then
Okay.
put k equals 2. We're going to go on till k equal to 3. So now let's put k equals 2. Tell me now, how will this work? Now you say I write, huh? K equals 2, you'll put it in this equation.
Mm-hmm. Okay. So 1 over 1 minus 0.4 e to the negative negative
J pi.
j pi, yeah, because yeah, that's it.
Yes.
Okay.
Now you'll put theta equal to pi here in this expression.
Okay.
So you'll get e to the negative j pi equals
Equals to cosine pi plus j sine pi.
minus j sine pi.
Oh, minus, yeah.
Sine pi is 0
Yeah.
and
What's
cos
wrong
pi
with
is negative 1. Use calculator for this. Later. You
Okay.
trust me right now.
Okay.
Okay, so that we can quickly finish this, right? E to the
Yeah.
negative j pi is going to be minus 1.
Okay.
All right. So what do you get here? 1 over 1 plus 0.4.
Okay.
And that answer is going to be 1 over 1.4.
Okay.
Now, once you get that, now let me clear some space. Oh shit, I need it actually.
So when we say 1 over 1 plus 0.4, where do we use the result of what I'm going to use for the calculator later on?
Sorry.
So I'm going to have to,
I use the result for e to the negative j pi,
uh-huh,
which was minus 1. You see that here?
minus 1, okay?
And then that's why this minus became plus.
So we don't need to use the minus 1 minus j.
For what?
Wherever it says cosine pi minus j sine. Oh,
Sine
because the j is
0.
0. Yeah, I'm okay. That's
That
fine.
becomes 0. All right.
Yeah.
So I'm going a bit faster because you will have anyways a recording of this.
Yeah. No, that's fine. It's good.
So that you can always go back and have a look at it.
Yeah. Okay.
Because I have said everything, so you will definitely rewind and see everything.
Okay.
So that's the advantage of recording. We can do a lot faster.
Okay.
Okay. So then this is 1 plus 0.4, which
Okay.
is 1.4.
Mm-hmm.
Okay. Now I have to clear some space. I can clear it over here. Okay. So now next we have to do k equals 3, right?
Yeah.
Okay, let's do k equals 3. Uh, if I put k equals 3, okay, I'll get x of 3. Then I put k equal to 3 in this.
Okay. Yeah.
We put that value and solve. Okay.
Okay. 1/1 minus
Right.
0.4
Hold on.
to the negative.
Hold on. 1.16, 1 plus 0.4j is going to be the answer. So what happens is it becomes a conjugate of this.
Okay.
You can solve and check later on.
Okay.
I encourage you to solve and check.
Okay.
But I know this.
So, is there a quicker way to do it based on what we've already solved, or do
Yes.
I just do the same exact steps?
No, there is a quicker way of solving as well.
Okay.
And we will do that after this. So basically, and I have to go from k equal to 0 to k equal to 3 anyways.
Okay.
And I've done that. So I've got like 4 values. You see, the first
Yeah.
value for k equals 0, I got this. Then for k equals 1, I got this answer.
Yeah.
Then k equals 2, I got this answer. And for k equals 3, I got this answer.
Okay.
And it's time to write down the final answer. And the final answer is going to be xk. And then write them down in a sequence. Let me write down vertical or horizontal, it's your call. But let me write down vertical. 1 over 0.6, the first value.
Okay.
Then the second value is going to be 1 over 1.16, 1 minus 0.4j. Then the next value is 1 over 1.4, this one.
Okay.
And next value is 1 over 1.16, 1 minus 0.4j.
Okay.
And I got these values at k equals 0, k equals 1, k equals 2, and k equals 3.
Okay.
That's my final answer.
Okay.
And done.
Okay. So that solves for the 4-point DFT, right?
This is the answer. This is the 4-point DFT. This x of k
Okay.
is nothing but DFT, which is over
And
here.
what about the DTFT? Where's that answer at again?
There was a DTFT in between that we got x of e to the j omega, which was
Uh-huh.
over 1 minus 0.4 e to the negative j omega. This was DTFT.
Okay, that's
DTFT is
DTFT.
here.
Okay.
DFT is over here.
Okay.
Okay, so now you just have to understand that. Okay, let me explain these things once again. Let me clarify a few things real quick before we go to the next one. Well, 1 minute. Let me choose a color also. Now, this is okay. Let this will, I don't know if this is 1 minute. The color has to be good. Let's use, okay, let's use brown. Do you know this is all time domain?
Yeah.
And do you know all of these are transforms?
Yeah.
Like Z transform, discrete time Fourier transform, discrete Fourier transform, all of them are transforms.
Okay.
So they basically do what? They convert into frequency.
Mm-hmm.
So this entire thing over here, they all are frequencies.
Okay.
Okay. So this was time. Then we took a transform, we got frequencies.
Okay.
And frequencies are in different form. One is Z, other is omega, and other is K.
Okay.
So now these three frequencies, what is the difference between the two? They're all related. Like Z equals e to the j omega. That's the relation of Z and omega. Sorry, R is also there. That's the relation of Z and omega.
Okay.
Then omega is equal to 2 pi k by n. That's the relation of omega and k.
Okay.
So we basically made use of all these relations. And from x of z, we have reached till x of k.
Okay.
That's what we did here. And I think that was your question also. Can you read the question again?
Yeah, it's find no, if a sequence is 0.4 raised to the n un, find its DTFT and 4-point DFT.
So we just did that.
Yeah.
Okay, and then there is a shortcut way of solving as well.
Okay.
Okay, where you can actually need not take the long cut. You can directly go from here to here.
Okay.
Okay, I can show you that shortcut as well. Okay, but then
Okay.
that's not really part of this question. I believe I have a video on this. So let me stop recording this for a minute, and I'll show you the